Hey, welcome back to my Introduction to Mathematical Proofs playlist. Today, we'll be introducing the idea of cardinality. So what is cardinality? Informally is the size of a set, or how many elements there are in a set. However, the key difference is this: we allow infinity to be a valid size. And while we can't quantify this with a number, this is what I believe to be the reason why we don't use the word size, and rather cardinality. Yeah, even I wasn't really told why we use the word cardinality, not size. Maybe it's like, oh, we wanted a cool math term. Maybe there's an actual reason. For example, if you have a set with 100 elements, well then its cardinality is 100. 1000 elements, cardinality is 1000. What's the cardinality of an infinite set? Well, we say that it's countable, or it has countable cardinality, or there are countably many elements in the naturals. And I don't really like the word countable here, because countable implies that, hey, we can count every number. It's not necessarily the fact that we can count every number, it's the fact that we can list every number, or enumerate through every element in the list, or find everything that we need to find. We can devise an algorithm that will literally find every single element. And the algorithm in this case is just counting 1, 2, 3, 4, 5, and so on and so on. Words that make more sense than countable is enumerable or iterable or listable, right? And despite the set being infinite in size, the idea is we can find an algorithm that finds everything, enumerates through the list, iterates through the list, lists every element, so on and so forth. Let's just run through a simple example. Let's look at the even numbers. We're going to denote this with E. Let E equal 2, 4, 6, 8, and so on, every even number. Well, what's the cardinality of E? Well, E is a subset of the natural numbers, and it's not equal. There's a reason why there's a line and it's dashed underneath. That's to explicitly state, hey, look, this is just a subset that is not equal. And even though E is a subset of the natural numbers, we can devise an algorithm to list every even number. Just start at 2 and keep adding 2. So, since it's an infinite set, we say that the cardinality of the even numbers is the same as the cardinality of the natural numbers. I want you to understand how weird this is. Usually, let's say in finite sets, if you have a set with 5 elements and a set with 4 elements, and set with 4 elements is a subset of the set with 5 elements, and they're not equal, well then we have like, oh, one's larger than the other. But that's not the case when it comes to infinite stuff. Infinity is really, really weird. But the thing that I just said isn't really a proof. Saying that, oh, it's infinite and we can list through it doesn't really necessarily prove that they have the same cardinality. Well, the idea is this. If the natural numbers are listable or countable or enumerable or iterable, and so is E, we should be able to find a way to map the even numbers to the natural numbers so that we can count them like kind of side by side. But this is exactly what a bijection is. We're mapping one to one uniquely. Let's start. Show that f that goes from the naturals to the evens, given by f of x is equal to 2x, is a bijection. And you can also do the bijection the opposite way, because the inverse is still a bijection. So if instead you were to do a function from e to n, well, then f of x would be half x. This would also be a bijection. So now let's just do it. Start with injectivity. We'll use the contrapositive, let f of x1 equal to f of x2. Then we'll show that x1 is equal to x2. Well, clearly it just works out. For surjectivity, let y just be an even number. Then we're going to let x equal 1 over 2. Now in this case, since y is an even number, we can divide it by 2 and get that x is a natural number. The reason this is important is because it's showing that, hey, x is in our domain, so that when we apply f of x and we get y, this is valid. Usually we don't have to do this when we're working with reals to reals, but in this case you do have to verify that it's in the domain. Your x is in the domain. Now here's a really cool part. If we just add 0 at the beginning, it's still the exact same cardinality, right? So now these were the conclusions that we drew from our pigeonhole principle episode last time, right? And our logic does make the exact same sense. If the cardinality of A is less than or equal to cardinality of B, we can find an injective function that goes from A to B. And you can do this in the exact opposite direction for surjectivity. If the cardinality of A is greater than or equal to the cardinality of B, we can find a surjective function. Now, the interesting thing here is we're going to let countable cardinality be greater than any finite cardinality. And then, yeah, it'll work, right? We can always find an injective function from like finitely many elements to countably many objects. 5 to everything, you should be able to find an injective function. Map everything to 5 elements, well, you should be able to find a surjective function. It makes sense. And remember how before we showed that, hey, if it's a bijection and has the same cardinality, we can do a similar thing. If you show that a function can never be surjective, then the cardinality of the domain, or the input set in this case would be A, would be less than the cardinality of B, the output set, the codomain. So f and the properties that f can have or not have will inform us on the cardinality of A and B, and yes, this even works for infinity. That's the real takeaway here. Now we can extend a pigeonhole principle in the infinite direction. Consider the following set: A is equal to 1, 3, 6, 10, 15, 21, 28, 36, 45, and so on. Pretty much we just add the next natural number and add it to it. What can we say about the ending digits of the elements in A without doing any sort of calculations? Well, A has countably many elements, the cardinality of A is equal to n. Kind of the takeaway is that because there's a dot 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 at the end, it's like, oh, hey, look, it just goes on forever, right? But you can actually prove this, and you should, just to get you comfortable with proving bijections and how that plays with cardinality. But what's interesting here is that there's only 10 possible ending digits. There's only finitely many of them. So is there any way that we can extend the pigeonhole principle to come up with any interesting conclusion that the regular pigeonhole principle doesn't take into account? And we can. The conclusion that we can come up with is that countably many elements from A will share their ending digit. And you might be like, wait, what? How does this make sense? Well, think about it. If we have finitely many boxes, in this case we have 10, but infinitely many pigeons, we just can't put a finite amount of pigeons in every single box. Then you can't have an infinite amount of pigeons. So one box must have infinite pigeons, and then every other box, it doesn't really matter what happens to them. We're thinking about the worst case. One box must have infinite pigeons. And here by infinite, we mean countably many. And this should make sense. If we only had one box and infinitely many pigeons, well, everything must go there. But if we had two boxes, well, let's think about it. If both boxes had finitely many pigeons, then where would the rest of the pigeons go? If we instead send pigeons labeled 1, 2, 3, 4, 5 to box 1, but then everything after 6 to box 2, well, box 2 has infinitely many pigeons, has the same cardinality. And you can extend this logic to every single natural number. So in our case, it's 10. And the consequence is pretty cool. Think about it. If you have an infinite set and you partition the infinite set into finitely many pieces, well, one of the pieces must have infinitely many elements from our set. So there's a really nice correlation between infinity and finiteness. Now, no more pigeons. We want to show that the cardinality of Z, or the integers, is equal to the cardinality of the naturals. So pretty much we're saying that the integers have the same cardinality of the naturals. And this is equivalent to finding a function from one set to the other so that f is bijective. If we can figure out how we list out every element in the integers, then we might be able to have a lead on how to construct our function. So usually we write out our integers with having dots on both sides. Dot, 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 -2, -1, 0, 1, 2, dot, dot, dot. But how do we list out every element? The first thing you might think of is, hey, why don't we count from 1 to infinity and then turn around when we get to infinity? But we'll never really reach infinity. Do you see the issue here? We can never reach infinity, so we can never end. There's no ending. Another way that you can think about it is, hey, if counting an element takes, let's say, 1 second, so 0, then a second later we do 1, and a second later we do 2, and a second later we do 3. If you had an infinite amount of time, would you be able to reach every element? If we count from 1 to infinity, well, no, we wouldn't be able to reach every element. We'd never get to -1, or we'd never get to 0, because we would never do this turnaround thing, because infinity never ends. So maybe you're like, what if we zigzag? So we start at 0, then 1, then -1, then 2, then -2, then 3, then -3, then 4, and so on and so forth. Well, then yeah, we will reach every single number, and we don't ever have this issue of turning around. For example, if you want the number -1,000,000, well then after enough time, if you just wait long enough and you list out a new element every second, well then after enough time you'll eventually get to 1,000,000. After an infinite amount of time, we should be able to reach everything. And the cool thing here is that because the dot 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 only goes in one direction, it kind of like acts like the natural numbers. So that's another way that you can think about this. So how are we going to map the natural numbers to the integers? Well, we can list out instead starting from 0 and just keep going onward. Same with n. So what if we just match them up like a sequence? So we send f of 1 or 1 to 0, then f of 2 to 1, then f of 3 to -1, and f of 4 to 2, and so on and so forth. Pretty much if we're to imagine n and z stacked on top of each other, we just link them up one by one. And this works. You will reach every single number, and we found a map from n to z that is a bijection. But how do we argue that it is a bijection? Well, usually it's nice to work with a definition for what f of x is. And while we don't necessarily need to define f of x, we might be able to informally argue like, hey, look, you can reach everything, and clearly everything maps. Like, yeah, you could say it's injective and surjective, but having f of x proves it without a shadow of a doubt. That's kind of what we want to go for. We really, really want to make sure that we're rigorous with everything we do. So we're going to define f as a piecewise function. If you know what a piecewise function is, good. If you don't, how it works is that we define f of x to be different depending on what x itself is. So how we're going to read this is that f of x is going to be equal to 0 when x is equal to 1. And we're going to define it to be x over 2 if x is even. And in all other cases, so x is odd and not equal to 1, we're going to define it as negative x minus 1 over 2. Now we'll show that f is bijective. And maybe think about why this would work. If you write out all the elements, see why this would work, and maybe try to prove it for yourself. See if you can figure out how to do this. Okay, so we're going to start with injectivity. And this is going to be a little annoying to do because when you're working with piecewise functions, you have to deal with all the different cases, but we'll just slowly work through it. Let x1 not equal x2, then we're going to have three cases. In the case that x1 is equal to 1, well then f of x1 is equal to 0. So if f of x2 is even, then f of x2 is not equal to 0 since we divide by 2. And if x2 is odd but not equal to 1, then f of x2 is equal to negative x minus 1 over 2, which is of course going to be less than 0. So that handles the case when x1 is equal to 1. Now, what about the case when x1 is even? Well, then we have that f of x1 is greater than 0. Then this means that x2 must be even, because as we showed before, if it's odd and not equal to 1, it'll be less than 0. But then we'll have the following. x1 is not equal to x2 implies that x1 over 2 is not equal to x2 over 2, which implies that f of x1 is not equal to f of x2. And now in the case that x1 is odd and not equal to 1, well then we know that f of x1 will be less than 0. So x2 must also be odd and not equal to 1. Then in this case, x1 not equal to x2, follow down the chain, divide by 2, and then we get f of x1 is not equal to f of x2. So in all cases, f is injective no matter how we pair up x1 and x2. Now let's go to surjectivity. We'll show that f is surjective. Let's let y be an integer. If y is equal to 0, then we claim that x is equal to 1 works, since f of x is equal to f of 1, which is by definition 0, which is by definition y. If x is positive, then x is equal to 2y would work. Note that this means that x is an even number and it's a natural number. Then f of x is equal to f of 2y. Now we apply the definition of it being even, which is half 2y, which is just y. Now, if x is negative, well then x is equal to negative 2y minus 1 will work. In this case, we'll notice that x is odd, and since 2y is less than negative 1, when we multiply both sides by negative 1, the inequalities will flip, so we have negative 2y is greater than 1. So this means that x is greater than 0. This means that x is a natural number since y is an integer and is greater than 0. It must be a natural number. Then f of x, we apply the definition, multiply algebra out, we get y. Clearly, f is surjective and therefore bijective, so the cardinality of n is equal to cardinality of z. Now, what's really annoying here is kind of like all the algebra, and it's like, okay, where did you come up with all of this? Maybe you can understand if y is equal to 0, then x equal to 1 would work. Maybe if it's positive, you understand why. But then why would the negative one work? How did you come up with x equal to negative 2y minus 1? Well, once again, we do the same strategy. We just invert the function. So we just invert x plus 1 minus 2 and take the negative of all of that. We just invert that. Now, here, two things are kind of different and two things you need to keep note of. When working with a piecewise function, we always have to deal with all the different cases. So we need to deal with all the cases of what the output could be. You have to deal with all the definitions of f and what x1 and x2 could be. Another thing you might have noticed is that, as I mentioned before, we show that x is in our domain. We've never really had to deal with this because the codomain and domain so far have always been R, and I'm just being extra careful. I'm just making sure that everything makes sense, because when you make mistakes haphazardly and you're not checking for every single case, that's when you're going to be like, hey, there's an issue with what I just did. And of course, if you have time, you should take your time to slowly understand what's happening. If you don't have time, then that's a different issue altogether. But once again, just be careful with your proofs. That'll be all for this one. I will see you in the next one.